Welcome to my projectbazaar.com.
Now we discuss about the product for active mode subclock power gating. Next we see the abstract for the product. Leakage power can be as dominant as dynamic power below 65 nanometer and poses the large source of power consumption in digital circuits during the active mode. Example for when the circuit is doing useful work, a number of techniques have been reducing the active leakage power dissipation. These include dual threshold logic when the use of high threshold logic gate is non-critical timing path and the active body biasing which raises of lower the threshold voltage of transistor for active power management. The effectiveness of power gating to reduce the leakage power has also been demonstrated during active mode. A finger gradually power gating has been proposed, which involves the disabling execution unit during the active mode. Similarly, a method of power gating is a part of a multiplier depending on the data with during the runtime was proposed in the recent work has demonstrated using the power gating on gradually akin of clock gating. This use of clock enables signal power gate to integrate the execution of processing level. All these methods attempt to reduce the power with minimal impact of maximum clock frequency. This power presents a technique called subclock power gating for reducing the leakage power during the active mode in low performance energy consumed applications. The proposed technique achieves the power reduction through the mechanism power gating the combination with clock period subclock and reducing the virtual supply to less than the voltage threshold rather than the shifting down completed as in the case of conventional power gating. To achieve this reduced voltage, a pair of NMOS and PMOS transistors are used at the head of foot of power gated logic for symmetric virtual rail clamping of power and grounder supplies. The subclock power gating technique has been validated by incorporating in with the ARM Cortex M0 microprocessor. Two set of experiments are done. The first experimentally validate the functionality of the proposed technique in the fabricated test chip and the second investigated utility of the proposed technique in example applications. Next we see the flow diagram for the product. Clock input signal CMOS design methodology for applied to our architecture designs. First of all, the clock input signal are the source of the clocking signal to apply the any type of combination or sequential based CMOS designs methodology. Our CMOS designs mainly consider for PMOS and NMOS transistor combinations with the type of any type of architecture. Our combination architecture mainly based on the inverter based designs architecture. Thus the inverting architecture logic to be controlled by the subclock power gating technique. This subclock power gating technique to apply the isolate architecturing functions. This isolation functions to isolate the clocking signal and based on our inverter input results. Thus the inverting results to be applied for the isolate logic and to control the subclock power gating technique the results produce the inverting architecture. So the combination with combinational architecture to be controlled for the input and output function for using the isolate architecturing functions. This isolating architecture function based on the subclock power gating source technique. This power gating to maintain the clocking signal based on our first combinational architecture result and the second combinational architecture results. These comparing results to be placed by the isolate functions and to maintain the clocking signal for our overall architecture. So we reduce the power consumption for separate clocking cycles to be replaced by the subclock power gating technique in our overall architecture. This subclock power gating to minimize the power consumption and to improve the system performance level. And finally we see the output for the product. This is our design for subclock power gating designs. First, the clock source to be applied for our design architecture, then to apply the inverting logic. Thus, the inverting logic to invert the clocking input signal based on our input data to apply the inverting results, and to subclock to be applied for isolate architecture. Then the power gating to optimize the clocking signal in our isolate architecture. Thus, the inverting designs to be passed on isolate functions and to apply the another one combination circuit based on our subclock power gating isolation section. This is the isolation section to maintain the clocking signal to process our second combination architecture results. Just to run the our architecture process, then to design the active mode processing results and to apply the clock signal to activate. Thus, the input to be activated in the inverting the logic and the output to be inverted. The output second to be passed on the isolate function to maintain logic is the override input signal and the clocking input signal based on our input, based on our clocking signal to be invert the output results for our the output logic. The second combinational architecture to maintain our output results based on our clocking signaling level. This is the output for timing diagram for our architecture designs. Thus, the inverting input to be applied for our input signal when the clock is equal to 1 positions, and the input to be passed on the another sections for 0 positions in our output results. Thus, the 0 position of input signal to be inverting the output results for 1 position for our architecture when based on our clocking activation signal. This the clock activation to be based on consider the override the another one source signal. Thus, the override to be activated. Thus, the clock to be passing. Then the input to be activation for the combinational architecture designs of architecture. This is the subclock passing for inverting designs and to control the combinational architecture. Then the overall process of subclock power gating architecture designs.